For most of human history, the universe was believed to be orderly, predictable, balanced, governed by laws that made sense. The stars moved as they should. Planets obeyed gravity. Galaxies, vast islands of light, were assumed to be stable systems drifting peacefully through space, bound together by gravity in a way that was elegant, understandable, and complete. For centuries, this belief went largely unchallenged, not because people weren't looking closely, but because everything they saw appeared to confirm it. In the early 20th century, astronomy was still a science of light. If you could see it, you could study it. If you couldn't see it, it barely entered the conversation. The universe, as far as humanity was concerned, was made of stars, gas, dust, and planets, objects that shone, reflected, or absorbed light. Darkness was absence, and absence was not considered something that could shape reality. That assumption would eventually collapse. But long before it did, a young girl was already learning how to question the sky. Vera Rubin was born in 1928 in Philadelphia, but her life would change when her family moved to Washington, D.C. From her bedroom window, the night sky became a living map. She watched the stars move, not casually, but systematically. Night after night, she noticed patterns. She noticed that the sky was not fixed, that it shifted, rotated, returned, that invisible rules governed the motion of light, and she wanted to know those rules. Unlike many children, Vera didn't outgrow her questions. They intensified. When she asked for a telescope and didn't get one, she improvised. She used what she had. She charted star positions by hand. She trusted observation. She trusted patience, and without realizing it, she was already doing science. But curiosity alone does not create a scientist. Opportunity does. And in the 1940s, opportunity for women in physics and astronomy was scarce. Not because women lacked ability, but because institutions lacked imagination. Vera Rubin enrolled at Vassar College, one of the few places where women could seriously study science at the time. She majored in astronomy, and when she graduated in 1948, she did so as the only astronomy major in her class. Even then, her interests were unconventional. Instead of focusing on individual stars or planets, she was already thinking about galaxies as systems, how they moved, how they clustered, how they behaved collectively. Questions most astronomers weren't yet asking. Her next step seemed obvious: graduate school. She applied to Princeton University, one of the most prestigious centers for astrophysics in the United States. But Princeton did not admit women into its astronomy graduate program. Not unofficially, not quietly, explicitly. The rejection had nothing to do with her grades, nothing to do with her ability. It had everything to do with her gender. That moment mattered because it revealed something Rubin would encounter repeatedly throughout her career. Science prides itself on objectivity, but institutions are human, and humans carry bias. Rubin adapted. She enrolled at Cornell University, where she earned her master's degree in 1951. There, she studied under leading physicists of the time, and it was at Cornell that she began thinking seriously about something radical: the large-scale motion of galaxies. At the time, astronomy focused heavily on individual objects, stars, nebulae, specific galaxies. But Rubin wanted to know how galaxies behaved collectively, whether there were patterns in their motion across the universe. It was an ambitious question, and a controversial one. When she presented early work suggesting that galaxies might not be moving randomly, but might show coherent motion on large scales, the response was dismissive. Some senior astronomers openly rejected the idea. Others simply ignored it. Her conclusions conflicted with accepted cosmological models. And once, again, Rubin encountered resistance, not because she was careless, but because she was early. She completed her PhD at Georgetown University in 1954, balancing research with family life, another burden her male peers rarely had to navigate. Even then, she remained focused on galaxies, on motion, on gravity, on the structure of the universe itself. By the time Rubin joined the Carnegie Institution of Washington in the 1960s, astronomy was changing rapidly. New telescopes were coming online. Spectroscopy was improving. Astronomers could now measure not just where stars were, but how fast they were moving. And this would change everything. To understand why Rubin's later discovery was so shocking, it's important to understand what astronomers expected to see. According to classical physics, gravity behaves predictably. The farther you are from a source of mass, the weaker its pull. This principle had been tested countless times in the solar system, in laboratories, in binary star systems. It worked. So when astronomers began measuring how stars moved inside galaxies, they expected something familiar. Stars near the center, where most of the visible mass is concentrated, should orbit quickly. Stars farther out, where there's less visible matter, should move more slowly. This relationship should produce what's called a declining rotation curve. Fast in the middle, slow at the edges, neat, elegant, comforting. But when Rubin began looking carefully, really carefully at spiral galaxies, that expectation collapsed. Stars near the center behaved normally, but stars farther out didn't slow down. They kept moving fast, too fast. At first, Rubin assumed something was wrong. Maybe the data was noisy. Maybe dust was obscuring light. Maybe telescopes weren't precise enough. So she did what good scientists do. She didn't announce a discovery. She looked again. She partnered with Kent Ford, whose spectrograph allowed for precise velocity measurements. Together they began collecting high-quality data across multiple galaxies. And as the data accumulated, a pattern emerged. Not once, not twice, but everywhere. No matter which galaxy they studied, no matter how far from the center they looked, the rotation curves were flat. Stars were moving at nearly the same speed, regardless of distance. This result was devastating to existing theory, because according to Newtonian gravity, galaxies with that kind of motion should fly apart. They didn't. They held together, as if surrounded by an enormous, invisible halo of mass. This wasn't speculation. It wasn't philosophy. It was measurement, and measurement doesn't negotiate. Rubin and Ford published their results in the late 1960s and early 1970s, including the landmark 1970 study of the Andromeda Galaxy. The implications were enormous. Visible matter, stars, gas, dust, could not explain the observed motion. Something else had to be there. Something unseen. At this stage, Rubin still did not claim to know what that something was. She was careful. She let the data speak, but the conclusion was unavoidable. Galaxies contain far more mass than we can see. This idea was not entirely new. Other astronomers had noticed anomalies in galaxy clusters decades earlier. But Rubin's work was different. It was systematic. It was precise. It applied not to rare clusters, but to ordinary spiral galaxies, including our own. For the first time, the problem was impossible to ignore, and the universe, as astronomers understood it, began to crack. this was the moment before the storm, before resistance hardened, before recognition stalled, before the word dark matter became unavoidable, before the universe officially broke. Scientific revolutions do not fail because of band data. They fail because people are invested in the world as it already exists. By the early 1970s, Vera Rubin's measurements were no longer isolated curiosities. They were consistent, repeatable, and deeply uncomfortable. Galaxies were rotating in ways that violated everything astronomers expected, and that meant one of two things had to be true. Either gravity itself behaved differently on galactic scales, or most of the matter in the universe was invisible. Both options were radical, but only one required admitting that astronomers had been missing something enormous for decades. The initial response was not outrage, it was something quieter. Dismissal. Rubin's results were described as interesting, puzzling, worth keeping an eye on. Rarely were they described as correct. In conference talks, her graphs were sometimes shown and then quickly moved past. In papers, her conclusions were cited cautiously, hedged with language that softened their implications, not because the data was flawed, but because accepting it was destabilizing. At the time, cosmology was built on a delicate balance of theory and observation. Newtonian gravity still worked beautifully in most contexts. Einstein's general relativity had expanded that framework, not replaced it. The idea that an entirely new, dominant form of matter existed, one that did not interact with light, felt excessive, extravagant, almost irresponsible. And when an idea feels that disruptive, the instinct is not to embrace it. The instinct is to contain it. Rubin felt this containment everywhere. Her work was scrutinized more harshly than similar work by male colleagues. Her conclusions were often framed as provisional, even when supported by overwhelming data. Her authority was questioned in subtle ways, not directly, but persistently. There was also the matter of access. Observational astronomy depends on telescopes, and telescopes are controlled by institutions with traditions, and many of those traditions had never imagined women as equals. Rubin was not always allowed to observe when she needed to. Time on major telescopes was competitive, and decision-making committees were overwhelmingly male. Sometimes her proposals were rejected without clear explanation. Sometimes she was granted access, but made to feel unwelcome once she arrived. In one observatory, the lack of a women's restroom was not an oversight. It was a message. You are not expected to be here. Rubin did not dramatize these moments. She rarely spoke about them publicly at the time, but they accumulated, and they mattered. Because science does not happen in isolation. It happens in buildings, in meetings, in review panels, in conversations where credibility is assigned or withheld. Meanwhile, alternative explanations for Rubin's data flourished. Some astronomers suggested that the observed velocities were artifacts of dust or gas obscuration. Others proposed that galaxies had unusual distributions of ordinary matter that hadn't yet been detected. Still others argued that gravity itself might need modification. These ideas were explored seriously, funded, debated, refined. And that too was telling. Modified gravity theories were no less radical than dark matter. In many cases, they were more radical. They required altering laws that had worked for centuries, yet they were often treated as intellectually safer. Why? Because they preserved the idea that all matter was visible. They did not require admitting that most of the universe had gone unnoticed, and psychologically, that mattered. Rubin watched this process unfold without protest. She did not accuse her colleagues of bias. She did not argue emotionally. She did not defend her work with rhetoric. She defended it with data, again and again and again. She expanded her sample sizes, improved measurement precision, collaborated widely, ensured her results were reproducible. And as the years passed, something subtle began to shift. Other astronomers started seeing the same thing, using different instruments, different wavelengths, different techniques. Radio astronomers, measuring neutral hydrogen, found that gas far beyond the visible edge of galaxies was also moving too fast. Galaxy after galaxy exhibited the same flat rotation curves. The anomaly was no longer hers alone. It was everywhere. At that point, resistance changed form. It became quieter, less confrontational. Instead of questioning whether the phenomenon existed, the debate shifted to what it meant. Dark matter entered the conversation, not as speculation, but as necessity. Not enthusiastically, reluctantly. Still, something important did not happen. Vera Rubin was not suddenly elevated. There was no moment of collective acknowledgement, no clear admission that she had been right all along. The field moved forward, but without fully carrying her name with it. This is how scientific erasure often works, not through denial, through diffusion. An idea becomes accepted, but its origin becomes blurred. Credit spreads out. Responsibility dissolves. History becomes vague. By the late 1970s, dark matter was appearing in review articles, in conference proceedings, in grant proposals, but often Rubin's role was mentioned briefly, or not at all. The mystery was now bigger than any one person, which made it easier to forget who had forced it into the open. Rubin noticed, but she did not retreat. Instead, she turned outward. She mentored students, especially women, especially those who felt isolated. She served on committees, advocated for fairness in telescope time allocation, spoke quietly but firmly about inclusion. She understood something that many scientists learn too late. Being right does not guarantee recognition. Truth moves forward, but not always evenly, not always justly. And yet, despite everything, Rubin did not grow cynical. She remained focused on the universe, on the unanswered questions, on the deeper implications of what she had uncovered. Because while the scientific community was still wrestling with acceptance, the universe itself was already moving on. Dark matter was not just a galactic curiosity. It was beginning to appear everywhere, in galaxy clusters, in gravitational lensing, in the large-scale structure of the cosmos. The invisible mass Rubin had revealed was not a detail. It was the backbone of reality. And as that realization deepened, the resistance that once seemed insurmountable began to crumble, not with an apology, not with a confession, but with silence, the kind of silence that follows acceptance. By the early 1980s, one thing was clear. Vera Rubin's data was no longer controversial. It was foundational. But the cost of that foundation, the years of dismissal, the slow recognition, the quiet resistance, had already been paid. And now, the question had changed. No longer whether dark matter existed, but what it was. And answering that question would reshape cosmology far beyond anything Rubin herself could have imagined. By the early 1980s, the argument was no longer about error. It was about scale. What Vera Rubin had uncovered was not a small correction to existing theory. It was not a refinement. It was a revelation about how much of reality had been missing from view. Once astronomers accepted that galaxies contained far more mass than they could see, the implications cascaded outward, rapidly and irreversibly. If dark matter held individual galaxies together, then it must also shape how galaxies interact, how they cluster, how they evolve over time. And that meant dark matter was not a local phenomenon. It was cosmic. To understand just how profound this was, scientists began stepping back, far back. They looked not just at galaxies, but at the structure of the universe itself, on the largest scales imaginable. When astronomers map the universe, they do not see randomness. They see structure. Galaxies form clusters. Clusters connect along vast filaments. Between those filaments lie enormous voids, regions nearly empty of matter. This arrangement is known as the cosmic web, and it stretches across billions of light years. The question was simple: how did this structure form? According to physics, structure requires gravity. Matter pulls matter together. But when scientists ran simulations using only visible matter, stars, gas, dust, the universe refused to cooperate. Structures formed too slowly. Clusters were too weak. The web never emerged correctly. But when dark matter was added, everything changed. In simulations that included dark matter, invisible mass collapsed first. It formed the scaffolding of the universe. Ordinary matter followed, falling into dark matter's gravitational wells. Stars ignited, galaxies assembled, clusters emerged. The cosmic web appeared naturally. Dark matter wasn't a detail. It was the framework, the invisible architecture on which everything else depended. This realization transformed cosmology. Dark matter became essential to every serious model of the universe. Without it, nothing we observe today could exist. Not galaxies, not stars, not planets, not us. Measurements from the cosmic microwave background, the faint radiation left over from the Big Bang, confirmed this picture. Tiny fluctuations in that ancient light revealed how matter was distributed in the early universe. And those fluctuations only made sense if dark matter was present in large amounts from the very beginning. By the end of the 20th century, a new consensus had emerged. The universe is composed of three main components: a small amount of ordinary matter, the kind that makes stars and people; a much larger amount of dark matter, massive, invisible, and gravitationally dominant; and something even stranger, dark energy, which drives the universe's accelerating expansion. In today's best measurements, ordinary matter accounts for about 5% of the universe's total energy content. Dark matter makes up about 27%. The remaining 68% is dark energy. But when we talk specifically about matter, things with mass, dark matter accounts for roughly 85% of it, which means everything you have ever seen, every star, every planet, every galaxy, every human, belongs to a small minority of what exists. This realization is deeply unsettling. For centuries, science assumed that visibility equaled importance, that what we could see defined reality. Vera Rubin's work destroyed that assumption. Dark matter doesn't shine. It does not absorb light. It does not reflect radiation. It interacts with ordinary matter almost exclusively through gravity, which makes it extraordinarily difficult to detect directly. Scientists have spent decades trying. Deep underground laboratories listen for rare particle collisions. Space-based observatories search for faint signals that might indicate dark matter interactions. Particle accelerators attempt to create dark matter in high-energy collisions. So far, none has produced definitive detection. And yet, despite this invisibility, dark matter's influence is undeniable. It bends light through gravitational lensing, distorting the images of distant galaxies. It determines how galaxy clusters move. It shapes the distribution of matter across the universe. Its fingerprints are everywhere, even though it cannot be seen. This paradox sits at the heart of modern physics. We know dark matter exists. We know how much of it there is. We know what it does, but we do not know what it is. Candidates have been proposed. Weakly interacting massive particles, known as WIMPs, axions, ultralight particles predicted by theoretical physics, sterile neutrinos, exotic particles beyond the standard model. Each idea is motivated. Each has been tested. None has been confirmed, which means Vera Rubin's discovery remains incomplete, not because it was wrong, but because it opened a door science has not yet fully stepped through. Rubin herself understood this. She was careful never to overstate conclusions. She did not claim to have solved dark matter. She claimed only what the data demanded, that most of the universe's mass is invisible, and that ignoring it was no longer an option. As dark matter became central to cosmology, Rubin's role grew clearer to those paying attention. Her work had not merely contributed to the field, it had redefined it. She had forced science to confront absence, to accept that the universe is governed by things beyond perception. This shift had philosophical consequences as well. It challenged the idea that reality is limited to what can be observed. It reminded scientists that humility is not optional, that nature does not owe us simplicity or visibility. For Rubin, this was not a crisis. It was an invitation to keep asking questions, to let data lead, even when it leads somewhere uncomfortable. By the time she reached the later years of her career, dark matter was no longer controversial. It was unavoidable. The invisible majority had reshaped everything. But even as the universe absorbed her discovery, recognition still lagged. Prizes remained elusive. Public narratives stayed incomplete. And time continued its quiet march forward. Soon, another reckoning would arrive. Not about evidence, not about theory, but about memory, and about what happens when someone changes the universe, and the world is slow to notice. Before we continue, take a moment. Stories like this don't survive by accident. They exist because people choose depth over speed, patience over noise. If you believe these stories matter, if you believe science should remember who changed the world, not just what was changed, do not forget to subscribe. There is a moment in many scientific careers when recognition feels inevitable, not because it is demanded, not because it is chased, but because the evidence has become undeniable. For Vera Rubin, that moment arrived quietly and then passed. By the late 1980s and early 1990s, dark matter was no longer a fringe idea. It was no longer controversial. It was built into the foundations of cosmology. Graduate students learned it as fact. Simulations required it. Observations assumed it. Entire research programs now depended on a phenomenon Rubin had helped force into the open. And yet, when honors were announced, her name remained absent. The Nobel Prize hovered in the background of every conversation about her work. It was never openly promised, but it was widely expected. Many astronomers believed her discovery ranked among the most important of the 20th century. After all, she had changed humanity's understanding of what the universe is made of. Few achievements go deeper than that. Officially, the explanation was technical. The Nobel Committee traditionally rewards discoveries that can be tied to a clear, isolated event. A particle detected, a signal measured, a phenomenon directly observed. Dark matter, despite overwhelming evidence, remained indirect. Its effects were visible. The thing itself was not. Rubin had shown that it must exist, but not what it was, and that distinction mattered. But this explanation never fully satisfied the scientific community, because history did not support such strict boundaries. Nobel Prizes had been awarded for ideas that were incomplete, for discoveries whose full implications were still unfolding, for work that required later confirmation. Yet Rubin's contribution was treated differently, more cautiously, more quietly. The deeper reason was harder to articulate. Vera Rubin had not discovered an object. She had exposed an absence. She had shown that most of the universe had gone unnoticed. The gravity had been misunderstood. That light was not the final authority on reality. Awarding that kind of discovery required admitting something unsettling, that science had been missing something enormous for a very long time. Institutions struggle with that kind of admission. There was also the question of visibility. Rubin did not cultivate power. She did not dominate academic politics. She did not build empires or command institutions. She did not insist on ownership. She let the data speak and stepped back. In many systems, that restraint is not rewarded. As years passed, conversations grew quieter. Speculation about prizes turned into silence. And time, as it always does, kept moving. Rubin continued working, continued mentoring, continued advocating for fairness and inclusion. But the window for formal recognition narrowed. In science, timing matters. Being right is not always enough. You must also be believed at the right moment. And that moment does not wait. Vera Rubin died in 2016 at the age of 88. With her death, the Nobel Prize became impossible. Not delayed, not denied. Impossible. The response from the scientific community was immediate and revealing. Tributes poured in. Articles acknowledged openly what had long been whispered, that her work had transformed cosmology, that dark matter would not exist as a field without her, that the absence of formal recognition was a failure, not of evidence, but of the system meant to honor it. But posthumous recognition is fragile. It carries no ceremony, no acceptance speech, no voice. It exists only as reflection, and reflection always arrives too late to be shared with the person it honors. Yet even as awards remained absent, Rubin's influence only grew. Because science does not forget the way institutions do. Every time a galaxy is modeled, every time a simulation runs, every time the structure of the universe is explained, her work is there, quiet, essential, unavoidable. The irony is sharp. The woman who proved that most of the universe is invisible became, in many ways, invisible herself. Her discovery reshaped reality, but recognition lagged behind truth, and that gap tells us something uncomfortable. Not just about science, but about how humans choose to remember. This chapter of Rubin's story is not about bitterness. She did not carry resentment. She did not define her life by prizes not received. But it is about cost. Because recognition is not just personal. It shapes history. It decides whose stories are told, whose names survive. And for decades, Vera Rubin's name hovered at the edge of one of the greatest discoveries in modern science, close enough to shape it, but far enough to be overlooked. But history has more than one way of correcting itself, even when institutions fail. even when recognition arrives too late. And in the years following Rubin's death, that correction began to take shape. Slowly, deliberately, and permanently. After Vera Rubin, the universe did not become simpler. It became deeper. Because once dark matter was accepted, it refused to stay in one corner of astronomy. It spread into every serious attempt to understand reality at the largest scales. What Rubin had revealed was not just a missing ingredient. It was a new lens through which the universe had to be seen. By the late 20th century, cosmology had entered a new phase. No longer focused only on cataloging objects, it turned toward explaining structure. Why galaxies look the way they do. Why clusters form where they do. Why the universe has a web-like architecture instead of a smooth distribution of matter. Every one of those questions led back to dark matter. One of the most important confirmations came from gravitational lensing. According to Einstein's general relativity, mass bends space-time, and space-time bends light. That means massive objects can distort the images of galaxies behind them. Astronomers began measuring these distortions, and they found something striking. The amount of bending often far exceeded what visible matter could explain. The light was being bent by mass that could not be seen. Dark matter halos revealed themselves not through brightness, but through gravity. This was crucial, because gravitational lensing does not depend on assumptions about how stars move. It is geometry. Light either bends or it doesn't. And again, the conclusion was unavoidable. There was a far more mass present than light accounted for. Galaxy clusters told the same story. When astronomers measured how fast galaxies moved within clusters, they found velocities so high that the clusters should have dispersed long ago. They hadn't. The clusters were bound by enormous reservoirs of invisible mass. The same phenomenon Rubin had observed in individual galaxies was playing out on vastly larger scales. Then came precision cosmology. Space missions like COBE, WMAP, and later Planck measured the cosmic microwave background with extraordinary accuracy. This radiation, released about 380,000 years after the Big Bang, contained a snapshot of the early universe. Tiny temperature fluctuations encoded information about the universe's composition. And when scientists analyzed those fluctuations, they arrived at a consistent result. Ordinary matter alone could not explain the observed patterns. Dark matter had to be present, in large quantities, from the very beginning. By the early 21st century, the picture had stabilized. The standard cosmological model, often called lambda CDM, emerged. In it, dark matter plays a central role. It drives the formation of structure. It explains galaxy rotation. It accounts for gravitational lensing. It shapes the cosmic web. Without dark matter, the model collapses. And yet, the most unsettling fact remained. Despite its central role, dark matter still had no confirmed identity. Decades of experiments had narrowed possibilities, but none had crossed the line from inference to detection. This uncertainty did not weaken Rubin's legacy. It strengthened it, because it meant her discovery was not the end of a story. It was the beginning of one of the greatest scientific quests of the modern era. Today, physicists pursue dark matter on multiple fronts. Deep underground detectors search for rare interactions between dark matter particles and atomic nuclei. These experiments are shielded from cosmic radiation, buried beneath mountains or kilometers of rock. They listen for silence and hope for a whisper. Astronomers search the sky for indirect signals. gamma rays, unusual emissions, patterns that might indicate dark matter particles annihilating or decaying. So far, the results have been tantalizing but inconclusive. Particle physicists push accelerators to higher energies. If dark matter particles can be created in high-energy collisions, they might reveal themselves through missing energy, momentum that vanishes without explanation. Again, the evidence is suggestive, but not definitive. What has changed is not confidence in dark matter's existence. That question is settled. What remains open is its nature. Is it a single particle? A family of particles? Something entirely different from what current theories predict? Some physicists have proposed that dark matter may interact through unknown forces. Others suggest it could be a manifestation of extra dimensions. Still others revisit modifications to gravity, but now constrained by decades of data Rubin helped inspire. Every path forward passes through the evidence she made unavoidable. There is also a growing recognition of what Rubin's discovery represents philosophically. Dark matter is not just a scientific puzzle. It is a reminder of limitation, of humility, of the fact that reality is not obligated to align with human intuition. For centuries, light defined knowledge. If something emitted light, it could be studied. If it didn't, it barely existed. Rubin overturned that assumption. She showed that the most important structures in the universe do not announce themselves visually. They reveal themselves through influence, through effect, through what they make possible. This insight extends beyond astronomy. It reshapes how science approaches the unknown. It encourages patience, careful measurement, and a willingness to accept that absence can be as meaningful as presence. As the field evolved, so did the recognition of Rubin's role. Slowly, quietly, but steadily. Her work became standard reference. Her name appeared more frequently in textbooks. Her contributions were acknowledged more openly. Not through prizes, but through dependence. Because modern cosmology cannot function without her discovery. And perhaps that is the truest form of recognition. Not a medal, not a ceremony, but indispensability. As new generations of scientists enter the field, they inherit a universe forever changed by Vera Rubin. They do not question whether dark matter exists. They begin from that fact. They build on it. They search beyond it. In that sense, Rubin achieved something rare. She did not just add to science. She redefined its starting point. But even as her influence spread across equations and simulations, something remained unresolved. How would history remember her? Would her name remain attached to her discovery? Or would it fade, as so many foundational contributors' names have faded before? That question would not be answered by experiments, or equations, or observations. It would be answered by memory, and by a decision yet to be made. There is a kind of justice that does not arrive on time. It does not come with applause. It does not come with medals. It does not arrive while the person it honors is still alive to see it. It arrives later, quietly, permanently. Years after Vera Rubin's death, astronomy faced a decision. A new observatory was nearing completion, one of the most ambitious ever built. It would survey the entire visible sky again and again. It would track billions of galaxies. It would measure how light bends across the universe. It would map the invisible structure that shapes everything we can see. This observatory existed for one reason above all others: to study the universe Rubin had revealed. There were many possible names. Names of benefactors, names of places, names of power. Instead, the scientific community chose something else. They chose truth. They named it after Vera Rubin. The Vera C. Rubin Observatory is not a monument in the traditional sense. It does not celebrate victory. It does not declare a conclusion. It stands as an acknowledgement that the universe we now study, the universe we now simulate, measure, and try to understand, only became visible because one woman refused to ignore what the data was telling her. This observatory will not magically solve dark matter. It will not suddenly reveal what the invisible majority is made of, but it will do something just as important. It will ensure that Vera Rubin's name can never again be separated from the structure of the cosmos. Every map it produces, every dataset it releases, every discovery built on its observations will carry her legacy forward. Not as a footnote, but as a foundation. There is a profound symmetry in this. Rubin spent her life proving that the universe is held together by things we cannot see. And for much of her life, her own role in that revelation remained unseen. But truth has weight, and over time, weight bends history. Her work changed how humanity understands gravity, how galaxies form, how structure emerges. It forced science to confront its own limitations, to accept that light is not the final authority on reality, that absence can have mass, that darkness can shape everything. Yet perhaps her most enduring impact lies beyond equations and models. Vera Rubin changed who could belong in science, not through slogans, not through confrontation, but through persistence, through excellence, through presence. She mentored relentlessly. She advocated quietly. She opened doors simply by walking through them and refusing to leave. She once said that the world would be a better place when women were not remarkable in science, just present, not exceptional, not symbolic, simply there. That world is still being built, but it is closer because of her. The universe did not change because Vera Rubin observed it. The universe was always this way. What changed was us, our understanding, our humility, our willingness to accept that what we see is not all there is. Vera Rubin did not solve the universe. She did something more important. She showed us how much of it we do not yet understand. And she gave science permission to keep asking questions that feel uncomfortable, questions that challenge certainty, questions that refuse to go away. In the end, her story reminds us of something essential. That discovery does not always come with recognition, that truth does not always arrive loudly, and that the most important forces, whether in the universe or in history, are often invisible, until someone has the courage to measure them. If you're still here, thank you. This channel is built for those who believe knowledge is worth the time it takes to uncover. If these stories resonate with you, subscribing helps keep them alive. Share this with someone who looks beyond the surface, with someone who understands that truth doesn't always announce itself, with someone who believes memory matters. The universe is held together by the unseen. So is our history. Until next time, stay curious.